the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through matrix operations, matrix arithmetic, matrix algebra. Specifically, you've just stepped into the idea of an inverse. And in this video, we're going to focus pretty much on the inverses and computing the inverses of 2x2 matrices. By the way, this video can also be watched by those who are in pre-calculus if your pre-calculus class requires matrices, which is a common prerequisite, honestly. Anyhow, computing the inverse of a 2x2 matrix. To have this conversation, we're going to have to introduce a somewhat new quantity in mathematics called the determinant. And the determinant is not only existent for 2x2 matrices, we're just defining it here for a 2x2 matrix, but as we move forward, we're going to grow that definition to cover larger and larger matrices. The main thing I should say up front about computing determinants is that it can only be done for square matrices. But again, let's go ahead and just focus on a 2x2 matrix. The determinant of the 2x2 matrix A, which is written here as A, B, C, D, very nice way of writing it, is defined to be the notation det of A, that means the determinant of A, and it is actually just a scalar quantity, A times D minus B times C. And here's how most students, and actually myself, think of it. It's A times D, so that's a product there. And then in red, I'll show the subtraction, minus B times C. So again, A times D minus C times B, or B times C. It doesn't really matter how you say that because scalar multiplication is commutative. Anyway, AD minus BC. Now that we have that written down, let's figure out why that's so important, other than just giving us a number to assign to any given matrix. And in fact, before I do, let me just compute the determinant for a single matrix right now. Actually, let's do it for two matrices. So we had that matrix A in the previous video, and the matrix B, which we found was its inverse. Let's go ahead and compute the determinants of both of these matrices. The determinant of A, again, is AD, the product, minus the product BC. Again, scalar multiplication is commutative, so I could have written that as 2 times 1. It doesn't really matter. But that determinant ends up being 3 minus 2, or 1. Let's go ahead and compute the determinant of B. And you see that's going to be, again, A times D, which is 1 times 3, minus B times C, which is negative 1 times negative 2. And this case, again, you actually get down to the determinant being 3 minus 2 again, which is 1. I don't want you to think that determinants of invertible matrices are always 1. That's actually not true. However, in this case, it just happens to be because the matrices I chose. Determinants are very, very fascinating quantities because they tell us something about the matrix in the background that may not be ever shown to you. They're highly associated with what you eventually have to divide the linear system by in order to solve the linear system. So we'll see that later on. You don't need to know that right now, but that's just something that I find fascinating about determinants. And here we are in this material with our very first theorem. Now it says theorem 4 because my previous section of material had 3 big theorems in it. But in this unit, or this section of material that we're currently in, which is all about the inverse of a 2x2 matrix, we really haven't seen a theorem yet. But here we go. We're going to let A be that standard matrix. I shouldn't use the word standard because that phrasing, standard matrix, is generally linked to a transformation. So here's our basic matrix right here. A is equal to A, B, C, D. If the determinant is not 0, then A is invertible. And actually, to compute the inverse, you would use this formula right here. I'll say it out loud, although to be very honest with you, it probably just helps just looking at it. But it is 1 over the determinant. And remember, this is assuming that the determinant is non-zero. So the inverse is 1 over the determinant times the matrix. Instead of A, B, C, D, we have swapped A and D. And this is how I would say it when I was a student. We negate B, and C. And that happened to work very well for me when I was a student, to swap AD and negate BC. And of course, out front, you have the reciprocal of the determinant of your original matrix, and that would be A inverse. Now, if that's true, which it is, by the way, but let's just pretend as though we're questioning it. Man, is that true? I just don't know, right? But if it is true, then it should make sense that if the determinant is 0, then A is not invertible. That is, the A inverse does not exist. Well, it sort of looks like that should be true, because if the determinant is 0, then, well, you can see right there, you'd have division by 0. So it kind of makes sense that this little condition here, if the determinant is 0, then the inverse doesn't exist. But what we're going to do right now is prove this theorem. It's a little bit bulky, but we could totally do it. To do this proof, I'm actually going to start with the very first piece right here. We're going to let A equal that matrix, and we're going to let A inverse equal 1 of the determinant of A times the matrix D negative B negative C A. And what we're going to show is that A times A inverse is the same thing as A inverse times A, which is the identity matrix. Part of my proof, I'm going to go ahead and just note here that the determinant of A is, by definition, AD minus BC. That's just going to allow us to use that property or that right there without having any conversations about it in the future. Let's go ahead and figure out what A times A inverse is. Now, when I say A times A inverse, I hope you don't think that I'm assuming that that notation right here means that I automatically know it's the inverse. I'm trying to show that it's the inverse, but they just happen to have chosen that notation, which is convincing me that it is the inverse, but we're going to prove it is. So there's A times A inverse right there. We happen to know by a property of matrices that I can move this constant out to the front. And there we have that right there. Now I'm going to perform the matrix multiplication. We get to this point right here, and you'll notice that at least in the first row, second column, and second row, first column, those zero out. And we know via scalar matrix multiplications that we can bring this scalar on the inside and multiply each entry of our matrix by that 1 over AD minus BC. That will result in the 2 by 2 identity matrix. Now let's go ahead and show it the other way around. This time I don't have to actually factor the scalar out front because it's done for me. Performing the matrix multiplication, cleaning up that BD minus BD and the negative AC plus AC. And I used a property of arithmetic there by just commuting this addition. So writing AD minus BC instead of negative BC plus AD. And now I'll go ahead and multiply each entry within this matrix by 1 over AD minus BC. When you do that, you again get the 2 by 2 identity matrix. So we've shown that A times that symbol, which we shall call A inverse, is equal to A inverse times A, which is equal to the identity matrix. Therefore, by definition, A and A inverse are inverses of each other. So that satisfies actually the first part of this theorem. If A is ABCD, and if we define A inverse to be 1 over the determinant of A times this D negative B negative C A, again, how I say that is I swap and then negate. It turns out that matrix you get, which we have A with a superscript of -1, is the actual inverse of A. And that's perfect. So this chunk right here is done. We can check that, it's over with. Now we can move on with life. Now, as is the case sometimes in mathematics, when you're taking a look at the next piece you want to prove, or maybe a theorem you want to prove, there is something you haven't learned yet that is required for that proof. And that is actually the case here. We need to learn something first before I can come back to this and actually prove this statement. Basically, the thing we need to learn first is that matrix equations, which have coefficient matrices that are invertible, must have unique solutions. And once we have that, we can come back to this and prove the second part, that if the determinant is 0, then A is not invertible. But before we get there, let's actually just get some practice finding the inverse of an actual matrix. Notice in my example here, I don't even have a matrix written, and that's because I just want to do this off the cuff. So let's go ahead and create or invent a matrix, and let's find the inverse of this matrix. Now, because I created this, it's very often the case when you magically create a matrix that its inverse is going to be ugly. That's just how it works. Inverses are generally not beautiful. But let's go ahead and see this in action. B inverse, if it exists, is going to be 1 over the determinant of B times the matrix that is built from the matrix B. We're just going to swap these two entries and negate these two entries. Let's go ahead and do that. Well, that's sufficiently negative, isn't it? We swapped the -2 and the -1. Perfect. And then we negated the off column or off diagonal. Let's compute the determinant of B over here. Again, that's the product of this diagonal minus the product of the off diagonal. Again, sufficiently negatively ugly. And there we have the inverse of B. Very fast to find. One thing I do want to mention is if the fraction out front is nice enough, you could go ahead and distribute that into all the entries of that inverse matrix, or I'm sorry, of that matrix altogether. That's called the inverse. So you could distribute that in if you wanted to, just depends on your instructor. In this case, the fraction is ugly enough that I'd probably leave it out, but if you're bothered by that, I will move it inside. And that actually showcases how ugly inverses can look. They're very, very ugly, or they can be very ugly. Sometimes they can be beautiful, but most of the time they're just fractional messes. So here we are at that theorem that allows us to prove the second half of Theorem 4. Notice this is Theorem 5, which occurs after Theorem 4, but what are you going to do, right? So here's the theorem, unique solutions via invertible matrices. Really a very powerful theorem. And it states the following. If A is an invertible square matrix, which by the way, all invertible matrices have to be square, so that little n by n piece there is kind of redundant. But anyway, if A is an invertible n by n matrix, then for each B in Rn, the equation AX equals B has a unique solution. And by the way, that unique solution is X equals A inverse B. That is incredibly powerful. In fact, so powerful, I'm going to avoid the proof just for a moment because I want to drive home the idea of what this means. Imagine you're back in an algebra, a regular old algebra class, and you're asked to solve 3x is equal to 6. Well, one thing that you know to do is to divide by 3. But if I told you you don't have the ability to divide by 3, but you do have the ability to multiply by a multiplicative inverse, then you would say, great, I'll multiply both sides by 3 inverse. Now just note here that when I multiply both sides by 3 inverse, I'm really multiplying the left part of both sides by 3 inverse, because to relate it back to matrix multiplication, we know for certain that how we multiply two matrices is very important. If you multiply on the left, that might be different, and usually is, than multiplying a matrix from the right. So what I'm doing here is specifically choosing to multiply this 3 inverse right here, because that will undo a 3. If I chose to multiply a 3 inverse on the right hand side, I'd be multiplying x by a 3 inverse, and I don't want to do that. But going down to here, you can see 3 inverse times 3, which we know as 1/3 times 3, is just going to return x. And then we have this 3 inverse times 6, whatever that may be, we know that's 1/3 times 6 is 2. But that same idea is what's happening here. Somebody says, I have a matrix equation, AX equals B, and because we don't have division, I can't say, well, divide both sides by A. That just doesn't exist with matrices. However, what we have just learned is that an inverse matrix might exist, and if an inverse matrix does exist, then we can multiply both left-hand sides by that inverse matrix. And if we do that, we know that if A and A inverse are inverses, then A inverse times A is the identity matrix, and the identity matrix times the vector x is just going to be the vector x. And actually, that's very close to the proof of it. In fact, that's pretty much the proof of it. With the exception that while we have shown x is equal to A inverse B, we haven't shown that that product is actually unique. Because again, a very important piece is that, yes, there exists a solution, x is equal to A inverse B, but now we need to prove that solution is unique. That's very, very important. So just assume that I've actually started the proof because that's really the first half of the proof right there. So let's go ahead and assume there's another vector such that A times that other vector is also B. And let's call this solution Y. Why? Why not? Well, then we know that A times Y is equal to B. And by the very same operations that we did before, we can multiply both sides by A inverse. We know A inverse times A is the identity matrix. And we know the identity matrix times that vector Y is just going to be that vector Y. And we arrive at this point right here, but we already know what A inverse B is equal to because we've already supposed that AX equals B has a solution X. So up here we've assumed X solves AX equals B, which means that X is equal to A inverse B. But now we're assuming that Y also solves that same equation. And if that's true, then we've proven that Y must also equal A inverse B, which means that Y must equal X, because again, they're both equal to the same vector, A inverse B. So thus, X must equal Y, or you could say it this way, Y is equal to X. And therefore, X must be unique because again, Y, we just created a brand new vector, but the only way that brand new vector can also solve AX equals B is if that brand new vector is equal to X itself. And that is the proof of that theorem. Very nice proof. QED, quod erat demonstratum. So we are completely finished with that proof. Very, very beautiful. So let's just go ahead and use an inverse to solve a matrix equation. So somebody comes in the room and they say, here's an equation, AX equals B. I don't know what X is. So let's suppose that this is the matrix equation they've handed us. If, and this is a big caveat, but if we can compute the inverse of the matrix A here, then we can rewrite this as X equals A inverse times the vector B. And that is a big fat if, right? We don't know if we can actually compute the inverse of this matrix, but we're sure gonna try. Let's go ahead and call this matrix A, because I kind of did, and this vector here B. And let's go ahead and try to find what A inverse is. Remember, A inverse is just 1 over the determinant of A times the matrix where you swap the main diagonal and negate the off diagonal. It's worthwhile to check that you've swapped and negated correctly, because that can, even though there's no arithmetic involved, that does throw people off. Let's go ahead and figure out what the determinant of A is. Again, it's the product of the main diagonal minus the product of the off diagonal. That's gonna be a -3 minus 2. And there's my inverse of A. I'm going to use that to figure out what our solution is. X is A inverse times B, B being the vector here, -2, -3. Now, one thing that a lot of students tend to do, and I don't blame you for doing this, is they take this fraction and they immediately just plug it in. They just multiply everything through. I'm going to tell you right now, you don't want to do that. Mainly because you're just going to create a lot of fractional arithmetic in the end. Let me show you what I mean by that. If we know that X is equal to A inverse, which is -1/5 times the matrix, -1, -1, -2, 3, times the vector B, well, I need to do this matrix vector multiplication. And the fact that there are no fractions in this matrix yet is very helpful. You could probably see that pretty easily. So let's go ahead and just do that multiplication without fractions in there. And by the way, I made this up on the fly. I did not like pre-compute anything or try to make things nice, but it actually does end up being nice. Now I'm going to move that fraction into the inside of this vector here. And that is the solution to that matrix equation above. You could test it out. If you imagine that X here is -1, 1, you could see that'd be a -3 plus 1, which is a -2. and it would be a -2 minus 1, which is a -3. That does work out. So this is a really, really, really powerful theorem that we've just used. The fact that given a matrix equation AX equals B, we can solve it just by finding out what the inverse to A is and saying X is equal to A inverse times B, that is super powerful. Now, I want to give you some advice before we continue forward. While most students rejoice at an algorithmic method to solve matrix equations, like X is equal to A inverse B, it should be noted that unless you're solving multiple equations where the coefficient matrix is always the same, but the right-hand side is different, so in other words, you're solving equations like solve AX equals B, then AX equals C, then AX equals D, and so on and so forth. Unless you're facing that situation, finding the inverse is a little more computationally heavy than you need. That is, in large situations where you're not dealing with a 2x2 matrix, but let's say a 4x4 matrix or something like that, it's actually easier to use row reduction techniques if somebody just hands you AX equals B and that's it. However, if they do hand you a 4x4 coefficient matrix A and a few right-hand sides, they just say, well, this matrix times some unknown is equal to a vector B, and the same matrix times a different unknown has to be some other vector C, and so on and so forth. If they give you, let's say, 5 different right-hand sides, it is to your benefit at that point to find the inverse of A, because then X would be A inverse times B, X would be A inverse times C, X would be A inverse times D, and so on and so forth down the road. And that's basically what I'm saying here. It's often, given a single problem, much faster just to use row reduction. But again, given multiple problems with the same coefficient matrix, highly recommend that you find the inverse. Again, we haven't found the inverse for anything beyond a 2x2 matrix, because finding inverses for larger matrices is not impossible. It's not actually super duper challenging. It's just a lot of accounting. You're keeping track of a lot of numbers. So let's go back to theorem 4 here, because I did threaten that we'd come back and actually finish the proof on this. So, well, here we are, and I'm exercising my threat right now. So we want to prove that if the determinant is 0, then A is not invertible. And this doesn't actually require us very much to focus on this picture right here. Instead, we're just going to focus on A itself. I'll scroll down for that. And I went ahead and wrote the definition of A again, just because we're restarting the proof by picking up on the second half of it here. So we're letting A equal A, B, C, D. And we're considering the fact that we want the determinant to be 0. Well, we happen to know one thing about the determinant of a 2x2 matrix. It is AD minus BC. And there are a lot of ways for this equation to become 0. For example, everything could be 0, right? A, D, B, and C could all just be zeros. That would make this true. It could also be the case that maybe let's say A and B are 0. If that were the case, then again, this equation would be true. Or it could be the case that C and D are 0. Again, if that were the case, then this would be true. It could be actually that A and C are 0. And that idea of testing through what A, B, C, and D can be is how a lot of proofs work when you're dealing with this proof. However, I'm going to do it a little bit differently because I like the way that I do this proof. So let's go ahead and make a note here, or make a mention that from Theorem 5, we know that if A is invertible, then the matrix equation AX equals B implies that X is equal to A inverse B, and the solution X should be unique. That's what Theorem 5 tells us. Specifically, if A inverse exists and we are working with the homogeneous equation AX equals 0, then X equals 0 must be the only solution. Remember, the solution should be unique if A is invertible. And that's how I'm going to show, or actually how to prove, the second half of this theorem. So let's go ahead and actually build a homogeneous equation. Again, if A is invertible, that homogeneous equation will only have the trivial solution, 0. So let's go ahead and see what happens. I went ahead and wrote it as an augmented matrix. And what I'm going to do is a little row reduction technique here. And this is something that, again, you might not see in your textbook. I don't know why they don't do this, but let's go ahead and just do this here. I'm going to take a negative C over A times row 1, and I'm going to add it to row 2. When I make that move, I'm assuming A is non-zero. We'll come back to that in a moment. Now what I'm going to do is multiply row 2 here by A. Remember, I'm assuming right now that A is non-zero. If I do that, I get the following. And remember what we assumed right from the get-go, that the determinant is 0, and therefore AD minus BC is 0. So if AD minus BC is 0, that picture that I've just highlighted is 0, and our coefficient matrix only has one pivot column, which means we have a free variable, which means there's an infinite number of solutions to AX equals 0, which goes against what we said a few moments ago. If we assume that A is invertible, then AX equals 0 should only have one solution, and that solution should be X is equal to A inverse times 0, or in other words, 0. But here we found that that is just not going to be the case. Therefore, A inverse does not exist. Now, all of that is predicated on one assumption here, and that one assumption is that A is not 0. But what if A is 0? And I wrote that right here. What if A actually is 0? Well, if A is 0, we can go back up to our original augmented matrix. We would get 0B augmented with 0, and CD, again, augmented with 0. And you may say, great, let me swap rows, and that looks like, and it really does look like, this has two pivots. So I should, or two pivot columns in the coefficient matrix, and so therefore it should only have one solution. However, we do have a condition that we need to keep intact. We have this condition right here, that A times D minus B times C must equal 0. So since A times D minus B times C must equal 0, the product AD must equal the product of B and C. And again, this is if A is 0, well, that would imply that 0 is equal to B times C. So either B is 0 or C is 0. Well, if B is equal to 0, just imagine what happens. We now are back to having a single pivot column, and we'll have an infinite number of solutions because we have a free variable. So obviously B can't be 0, so let's go ahead and put that back in. Well then, therefore, if B can't be 0, then obviously C has to be 0. Well, great. But again, that means we only have a single pivot column, and again, we have an infinite number of solutions. Therefore, A cannot be invertible. If it were invertible, we wouldn't get those infinite solutions. Thus, if the determinant of A is 0, A inverse just does not exist. And that is the second part of that proof. Now, if you read it in a text or somewhere like that, they go about it a different way, but this way is a very clean way, I think. Even though I didn't formalize it, I didn't clean up the notation, the fact is it does actually work very nicely. Now, I promise you we're almost out of this video. We just have this one last theorem, a really cool theorem, but this one last theorem to go through. And this is more of a theorem about the arithmetic, or the product style arithmetic with invertible matrices. So let's go ahead and consider two invertible matrices, A and B. They're both the same sized matrices. They're both n by n matrices. And I realized just before I was going to read this, that this part of the sentence is just not worthy of being there. So I'm just going to erase that, and I'm going to pick up at the back end of that sentence. Because we already know A and B were provided to us as invertible matrices, so therefore the following is true. A inverse, that is the inverse of A inverse, is A itself. Now that should make sense to most people. If you think about it in terms of numbers, 3 inverse, well, this is arithmetic, so we're allowed division in arithmetic. That would be 1/3 to the negative first, and of course, that just flips 1/3 and you're back to 3. So that's the mechanical view of it. It actually is the same for matrices, although you don't get division with matrices, so don't think you can adhere to that. The second property, A times B is still invertible. So if A and B are invertible, then their product is also invertible. And by the way, the inverse of their product is B inverse A inverse. So the inverse of a product is sort of the product of their inverses, but in reverse order. It's a commuted inverse product. So note, this is not A inverse B inverse. That is not what this is. It is actually the other way around. So that kind of throws people off. Just be aware of that. And then the last one, again, as long as A is invertible, then A transpose is also invertible. And the inverse of A transpose, well, that's a nice one. It's just the transpose of A inverse. That's a really nice one to do. And by the way, some of these are usually given as homework problems in a linear algebra course. So let's go ahead and prove part B here, that the inverse of the product AB is actually just B inverse A inverse. This one, again, is generally proven in a textbook, but it's nice to have somebody kind of talk their way through it. So let's take a look at A times B. And we're claiming that the inverse of A times B is B inverse A inverse. So let's go ahead and write that down. I'm not assuming right now that B inverse A inverse is the actual inverse of the product of A and B. I'm just seeing what happens if I were to multiply AB times B inverse A inverse. In fact, let me use different colors. Well, then we know from matrix arithmetic that this is going to be A times B inverse times A inverse, but we know if B is invertible, then B times B inverse is the identity matrix. And the identity matrix times A is just the identity matrix, or it's just A. And of course, that is going to be the identity matrix because we're assuming, again, that A is invertible, B is invertible, and that A inverse is the inverse of A, and that B inverse is the inverse of B. So we've shown that the product of our black matrix and our blue matrix is going to be the identity matrix. Let's go the other way around. If this product ends up being the identity matrix as well, then we will have shown that these two pictures are inverses of one another. When we get to this point, again, by the same arguments, A inverse times A is the identity matrix. And of course, the identity matrix times either B inverse or B is just either of those matrices, doesn't really matter. And then B inverse times B, well, that's the identity matrix. So we have shown left multiplication by AB against that blue matrix is going to be the identity matrix, and right multiplication by AB against the blue matrix is also going to be the identity matrix. By definition, AB and B inverse A inverse are inverses. That is, the inverse of AB must be that B inverse A inverse. That proof is done. There's not much to it. And that actually finishes it for this very long video. So I hope to see you in future videos, and I hope you have a wonderful day. Be a good human.
It's the system of equations. We must deal with them all. Solutions. And work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.